Today I'm going to talk about one of my favorite subjects, which is nuclear chemistry. And nuclear chemistry, and the term nuclear in general, refers to of or coming from the nucleus of an atom. And we've talked a lot now about subatomic particles and about the structure of an atom in general. And so now we're just going to focus on the nucleus, which is made up of protons and neutrons. And so those protons and neutrons, given certain circumstances, can be radioactive. And so we have atoms and we have elements on the periodic table that are radioactive elements. And so let's define some terms to start off with, and then we'll kind of address some concerns that come from radioactivity and radiation, and hopefully help eliminate some misconceptions about nuclear chemistry in general. So radioactivity is the emission of high energy particles or radiation from an unstable nucleus. So it's an emission, meaning that these things come from the nucleus. And the things that are emitted are high energy particles, and I'll explain what those are in a second, and radiation from an unstable nucleus. And unstable is kind of the key to this, and we'll talk about what that all has to do with anything in just a second. So radioactivity is the emission of high energy particles and radiation, and or radiation, it doesn't have to be both, from an unstable nucleus. And we often will think of the terms radioactivity and radiation as the same thing, but radiation just means energy that is emitted, right? Energy that is radiating. So you can have UV radiation, right? So the ultraviolet radiation that comes from the sun, for instance, is just sunlight, or infrared radiation. So you can have energy that comes from some sort of source, and it just has to be a wave, right? We talked about waves in the last chapter. So if it's emitted energy in general, it's radiation. It doesn't necessarily mean that it's radioactivity. So radioactivity is this unstable nucleus that emits particles or radiation, and radiation itself is just the energy part. So again, we often use the terms interchangeably, but they really do mean two distinct things. And radioactivity is the thing that we really need to be concerned about, because radiation can just be the visible light that we see, and that's not super dangerous to us necessarily, but radioactivity can be. And so the process by which these high energy particles and radiation are emitted is called radioactive decay. Radioactive decay. So it's a decay process, which means that the nucleus, again going back to nuclear there, the nucleus of an atom is going to break down or decay. And the result of this breakdown of this unstable nucleus is the emission of these high energy particles and radiation. So we'll talk about kind of the different forces at work in a nucleus that is unstable, but I really wanted to define some terms first. So radioactivity, radiation, and radioactive decay. These are kind of what we're talking about with nuclear chemistry in general. So now let's talk about different types of radioactivity. There's basically three major types. There's more than this, but we're just going to focus on the three types of radioactivity. And these three types have Greek names. They have alpha particles, we have beta particles, and we have gamma radiation. Okay, so alpha, beta, and gamma, which are the Greek letters there. So let me give those to you below, in case your Greek is rusty. Alpha, beta, and gamma. Gamma should be familiar because we've talked about the electromagnetic spectrum. In the electromagnetic spectrum, gamma radiation was the highest energy radiation. And so gamma radiation is just energy. And it's really high energy. It's really short wavelengths, high energy. It's the highest on the electromagnetic spectrum. And so because it's just energy, it doesn't have a charge associated with it. It's neutral because it's just energy. It wouldn't have a charge. Now kind of going up from there, so gamma is sort of the scariest of the three. If we go up to beta particles, again these are particles and not energy, so we can think about them as having mass and a volume. These beta particles are electrons, high energy electrons, that are emitted from the nucleus. Now that should make you stop and think for a second. Electrons emitted from the nucleus. Well, electrons aren't in the nucleus, so how can that be a thing? Well, electrons are not in the nucleus. You're correct, but sometimes in the process of radioactive decay, neutrons that are in the nucleus can be converted, and again, we're not going to get into the details of this, but neutrons can be converted into electrons and then shot out of the nucleus at really high energies. And these electrons that are emitted from the nucleus, these neutrons that become electrons that then get ejected from the nucleus, are called beta particles. Okay, so the details of that are not super important, but just to let you know. And because they are electrons, they go from neutrons to electrons, so they pick up a negative charge. And then the alpha particles are just helium nuclei, and we saw alpha particles before when we talked about Ernest Rutherford. Ernest Rutherford is the one who discovered the proton and the nucleus. So just as a reminder, here's our friend Ernest Rutherford. Ernest Rutherford was our New Zealand scientist. So Ernest Rutherford discovered the proton. He also predicted the existence of the neutron, and he did the gold foil experiment. In the gold foil experiment, he shot a beam of alpha particles at a piece of gold foil and figured out that there's something massive that deflects these alpha particles. So these alpha particles are made up of 2 protons and 2 neutrons, and so in essence they are a helium nucleus. Helium is He. And if you have a beam of these helium nuclei, or 2 protons and 2 neutrons, then you have a stream of alpha particles. And because things are made up of 2 positively charged things and 2 neutral things, then it has a 2+ charge, or a positive charge in general. Now, in terms of strength of these 3 types of radioactivities, even though I described them going from the ground up here, from gamma radiation up to alpha particles, the strength really increases going down. So we have an increasing strength. Beta particles are stronger than alpha. Gamma radiation is the strongest still. And to give you a sense of that, if I had some sort of radioactive source that was emitting all 3 types of these radioactive particles. So here's my radioactive source, some sort of box. And this thing is shooting out a beam of, let's start off with alpha particles. Let's say that this is my beam of alpha particles. Alpha particles can be stopped by something as simple as a piece of paper. They can also be stopped by something as simple as your clothing. And they can definitely be stopped by your skin. So alpha particles are not that strong, because if you had a beam of alpha particles shot at you, then your skin would be enough to block it from getting inside of you, which is a good thing. Now, if we have some beta particles, so these high energy electrons that are emitted from the source, so here's my stream of beta particles here. Beta particles can be stopped by a thin metal, and the thin metal that can stop them, kind of at bare minimum, is aluminum. So aluminum is Al on the periodic table, and aluminum is enough to stop beta particles. We usually think of aluminum as being a fairly lightweight, it's not very dense, It's pretty high up on the periodic table. It still acts as a metal in a lot of ways, but it just doesn't conduct heat as well, etc. So aluminum is kind of a weird one, and it will stop beta particles. Now if we have gamma radiation, remember that gamma radiation is energy, so I'm going to draw it as a wave here. So if we have this wave of gamma, then something to stop gamma radiation has to be much stronger stuff than your aluminum. And that stronger stuff is lead at the bare minimum. And lead is Pb. I always remember lead symbol, which is the Latin for plumbum, which looks like our modern word for plumbing, for instance. So, they used to have lead-lined pipes, which turned out to be a bad idea over time. But I always remember that we don't want lead in our peanut butter, if that helps you. Okay, so lead is enough to stop gamma rays, which is often why we hear that things are lead-lined. So in containment areas where there's radioactive waste, or places like Hanford down in Tri-Cities, Washington, Hanford will use lead-lined concrete containers to store radioactive waste materials so that the radioactive particles and energy are not released to the groundwater and the soil, and etc. We also will learn about a scientist by the name of Marie Curie, Madame Curie. And Marie Curie is one of the ones who studied radioactive materials first. She discovered the element polonium, and she also discovered radium. So she was Polish, and the element polonium is named after her home country of Poland. And she and her husband worked together to study radioactive materials. Marie Curie's lab is still so radioactive, and her or at least her lab space is actually not as radioactive, but her notebooks, her lab notebooks that she would keep all of her records in, have to be kept in lead-lined boxes because they're still so radioactive. So these things can stick around for a long time in terms of how dangerous they can be. But that being said, we think about radioactive materials in terms of their danger, but radioactivity is naturally occurring. And you will find radioactivity and radioactive decay all around you. So this is in everything that we interact with. We will find radioactive decay products in our rocks, we'll find it in our soil, we'll find it in water, it's in all the stars, it's all around us. And the radioactive material that is most prominent, at least on Earth, is called radon-222. Okay, so this is our isotope symbol here, where 222 is the mass number. So you might want to think about, with that mass number, how many protons and neutrons would be in this isotope of radon. But radon-222 is a radioactive decay product of uranium. Uranium is U on the periodic table. It's number 92. So uranium is up there in the higher levels of the periodic table. You'll note, if you look at a periodic table that gives you this type of information, that most of the elements, as you get higher and higher, more protons in the nucleus are radioactive, and we'll talk about why a little bit later. But when you have a radioactive material like uranium, and I know that uranium is something that you've heard of before, then it will undergo the process of radioactive decay, and as its nucleus breaks down, so as it emits things like alpha particles and beta particles and gamma particles, then it will form new materials. Okay, and these new materials that form are the decay products. And so we can find these things naturally occurring all around us, and we're actually exposed to radioactivity and radiation all of the time. And living on Earth means that we're exposed to radioactive materials and radiation, and all of this is called background radiation or background radioactivity. So there is some sort of background that we are all exposed to, and if we live in different areas of Earth, which we do, then the background will be slightly different in some places rather than others. And this has to do with things like what type of materials are in your soil. It has to do with things like your altitude. For instance, if you lived in Colorado, in those places that are much higher altitudes, much higher elevations, then you're much closer to the rest of the universe and much closer to these radioactive stars than those of us who are kind of at sea level. Right? So even living at different elevations and different altitudes on our planet are going to give us different background radiation levels. And depending on your behaviors and depending on your lifestyle, if you're up in plains more often than not, then that's going to give you a larger dosage of radiation in your lifetime, greater than the background, for instance, because you're going higher in altitude. And if you get more medical x-rays, that all kind of is going to impact your overall annual dosage of radiation. Okay, so radiation dosage. And your radiation dosage is just the amount of radioactivity that you are exposed to, usually over the course of a year. So we all have some sort of background radiation because of where we live and because of different factors of our environment. And then our dosage is how much we get kind of above and beyond that background. And so if you work with radioactivity, if you work down at Hanford, or if you worked at a nuclear plant, for instance, then you would get higher annual dosages. If you're an astronaut, you get higher annual dosages than those of us who stay closer to Earth's surface. So let's talk a little bit about, because we're scientists and we like to measure things, let's talk about some units for radioactivity. The one that your book mentions are REM, R-E-M in capital. So REM is a way to measure the damage that is done to human beings. It's a very practical measurement because of that. And we as human beings, of course, care about the damage that it does. So REM is not necessarily measuring the intensity of the radioactivity, but it's measuring the damage that it does to us. So just to give you a sense of this, 500 REM is a lethal dose. Again, to humans. And a lethal dose, and you've probably seen this term before, when you're talking about toxins or poisons in general, you talk about a lethal dose of something. A lethal dose is the amount that you need of a specific substance to kill off, for lack of a more PC term, 50% of the population. So what this means is you could get more REM than this of radioactivity and you could still survive. Or you could get less REM than this and you could die. I mean, it's just kind of an average. So 50% of the population, if they were to receive 500 REM of radioactivity all at one time, would die from it. Now again, just for basis of comparison, 200 REM is about the average dosage for chemotherapy. So I'm sure a lot of you guys know someone who has gone through cancer treatments or chemotherapy treatments or radiation treatments. And in chemotherapy, you're using radioactive materials to try to kill off the cancer cells before you kill the person. And so you're using an incredibly dangerous substance with the hope that you're going to target the right areas and kill off the cancer before you kill the person. Like I said, so 200 rem in one shot, and sometimes they have multiple times of those throughout the course of a week, much less a month. So this does some pretty serious damage, especially if you compare it to an all-in-one shot lethal dose. Now, that's all kind of doom and gloomy. You and I receive much less than 1 rem annually, usually. Annually, we receive less than 1 rem, which means that we don't usually even use the actual unit rem. We usually talk about it in terms of millirem or thousandth of a rem, because we usually are in kind of much less than 1 per year, unless we're doing something crazy like chemotherapy. Okay, so that's 1 unit of measuring radioactivity. Another unit that you will see when you're measuring radioactivity are called sieverts. And sieverts are just another way to measure radioactivity. We often will measure them in microsieverts. Around 2 sieverts is a lethal dose. So when you're measuring things like background radioactivity or background radiation, it's usually in the microsieverts or 1/1,000,000th of a sievert. So we don't get exposed to that much on a background level day to day. Another way to measure radioactivity is the becquerel. Becquerel. There's a C in there. So becquerels are named after Henri Becquerel, who worked with the Curies. Hopefully you can see the name better. This is that. I just snuck in the C there, sort of ineffectually. So Henri Becquerel was working with the Curies, and he was kind of responsible for their work with radioactivity, and he helped with that as well. So the becquerel is actually the SI unit. And you'll also see the Curie, which is abbreviated CI for reasons I'm not sure of. But Curies are also another way to measure radioactivity. So there's not a super standard way to do measurements with radioactivity. They each have their own values, and they each have their own things that they kind of focus on measuring. Like I said, the REM really focuses on the damage that's done to human beings. So those are just some units that you'll run across. Now I talked about ways that radioactivity is naturally occurring, and then we just kind of talked a little bit about, medical uses of radioactivity. But there is also a source of radioactivity in our homes that is pretty prevalent. So in your home, and give this a second of thought here, in your homes, what do you think is a source of radioactivity? And here are the usual answers I get to this question. I hear cell phones a lot. Maybe you said cell phones when you were thinking to yourself. I've heard microwaves. I've heard televisions. Okay. And there's a problem with all three of these. The first is that none of those things are radioactive, but they do emit some amount of radiation, right? So we're talking about energy that is emitted, radiation that is emitted, not radioactivity. So these things are not radioactive. Okay, so if we think about cell phones and televisions, those both emit radio type frequencies, radio waves, which are types of energy, which could be radiation. Microwaves are a type of energy, but they are not radioactive. Okay, they're not undergoing radioactive decay. They do not have radioactive materials within them. Now there is an exception to the TVs. The old CRTs, which are cathode ray tube TVs, they do have a little bit of radioactivity associated with them. But the place that's most radioactive in your home, given that you have a normal home, is actually your smoke detector. And your smoke detector, the way that it works, if you looked at the inside of your smoke detector, so here's a schematic of your smoke detector. It's probably more round than this, but forgive my drawing. Inside your smoke detector is a slight radioactive material. So let's draw a little radioactive sign here. Slightly radioactive. And it's a radioactive isotope of an element called americium. And so I have some americium-241 that is present, and that's my radioactive symbol there. My americium-241, which is present in your smoke detector. And this radioactive material emits alpha particles, and it will have some sort of detector in it, detector within a detector. And as this thing is emitting a beam of alpha particles to the detector, so long as the detector receives that beam of alpha particles, then everything is just fine. Okay, so these alpha particles, again, are these 2 protons, 2 neutrons at the helium nucleus. So this americium-241 is emitting these alpha particles. It's hitting the detector. The detector does not go off. Now, you light something on fire, or maybe you overcooked your toast, and then the smoke from your toast comes rolling out of the kitchen and comes in and then gets up into your detector. And remember, to block an alpha particle, you just need a piece of paper. So if you picture smoke particles in the air, smoke particles are just particles of debris, burnt whatever, burnt wood, burnt paper, burnt toast, whatever it is that's in the air. The reason that smoke looks thick and opaque, that you can't see through it, is because there's stuff in the air, and that stuff is enough to break that line of alpha particles. So it breaks this line of alpha particles, and the alpha particles no longer reach the detector. And if they don't reach the detector, then the detector will go off. And then you have to get up on a chair, and then you whack it down with a broom, etc. Okay, just like the rest of us. So the most radioactive thing in your home is not your cell phone, not your microwave, not your television. It is actually your smoke detector, which we all have. Okay, and if you have any questions on this, don't hesitate to ask, and I'll talk to you guys again soon.